anyways, as I say, thanks very much, Bob. I did see your message to Rob, and having a little bit more spare time than the group down there. So in lieu of you all coming to visit, which I'm sure will be possible in the future, I thought I'd give you a quick run through about what goes on down there, and probably more importantly for where I used to come from, justifying why we do it, why that's taxpayers' money, etc., going into that. So just a little bit about myself. I grew up around Salisbury, which is not so far from you. I was at school there, dead keen on astronomy, and actually, while doing A-levels, wrote to the Royal Greenwich Observatory in Herstmonceux, and they were taking on very junior staff then, and I got an interview with the Astronomer Royal, as was then, and got this job, which with the understanding that I'd be doing a degree and beyond during the work there, so which was a great environment to be allowed to do sort of night school and training during my time. Worked in the solar department first off, so I had access to these wonderful telescope for looking at solar white light and also H alpha for solar storm monitoring, etc. So really, I'm extremely lucky to have got straight into doing astronomy as a very junior person at the time. And then we got involved in the laser ranging project, which we'll talk more about in the early 1980s, and I was moved into that group from what had been occultations before that. And then the IGO closed and moved to Cambridge, which is why I'm now speaking to you from a village just north of Cambridge. But the last 15 years or so, I've been regularly commuting down to Sussex and being in charge of the group and developing some other hardware and software that we do down there. So, okay, so without further ado, I'll share my screen and see if I can find this. Okay. Hopefully that's there.
Yep.
Okay, I'll probably close my camera off if I can. No, I'll leave it on. Okay, so yes, thanks again, Bob. And I would like to just talk about what happens in Sussex and in the wider environment, the wider community doing this sort of satellite tracking work that goes on down there. And it's all in the name of geodesy, which is the study of the Earth's shape, gravity field, and orientation in space. So just going back to historical sort of area, there was always a fascination with determining the size of the Earth. So 300 BC, Aristotle thought that the Earth was pretty big, too big to move. That was their sort of feel about it. But then 50 years later or so, Eratosthenes of Cyrene, whether he actually did this experiment, but he used some simple geometry to estimate the circumference of the Earth, knowing the fact that the sun at the solstice was in the zenith in Cyrene, and he was able to measure the distance between those two, Alexander and Aswan, Cyrene, and therefore get the difference in the angle of the sun when it was close to the zenith. And he came up with an angle of 7.2 degrees. Adding the distance between these two towns, estimated the size of the Earth to be about 46,600 kilometers, which is what we now know. It's 40,000 and a bit kilometers. So he was within about 15%. And then moving forward then to the early space age, a huge amount of dedicated survey work went on after that point, where by survey work, a good estimate of the shape of the Earth was done. But then once we had the first satellite launched, the Sputnik, a new value for the fact that the Earth wasn't spherical, it was flattened, was derived from measurements of satellite orbits. So that was really the beginning of satellite geodesy, where King Healy and Merson from Britain measured the flattening of the Earth, and it was a factor of 1/298.1. So the polar diameter is about 50 kilometers less than the equatorial diameter, which is a big number. And the technique that King, Healy and Merson used was to measure the perturbations of satellites. So if they assumed a satellite was in orbit around a spherical Earth, they were able to determine the satellite orbit, but they noticed that there was a shift in the node of the satellite. So using ground-based observations compared to those predicted orbits, which is where we are now with using observations to compare with theoretical position of the satellite. So these observations then showed that the orbital planes were processing along the Earth's equator. This is the theory that was developed. So this precession, no dot there, is a function of the flattening, J2, which is a measure of the flattening of the Earth. And it depends on the inclination of the satellite's orbit, which is the I in that simple equation there. That is basically the underlying equations of space geodesy. And then there was then followed decades of satellite measurements, primarily actually to improve measurements of improved models of the gravity field. So they're using optical camera observations and radar observations of application satellites, whatever was up there, in fact, including surveillance, weather satellites, etc. And most of the observations, certainly the optical observations, were carried out by amateur astronomers who knew the sky so well and were able to time the points, the instants at which satellites moved in front of or close to or bisected clusters of stars or groups of stars that they knew. So they were able to record time accurately and position. And then there were dedicated geodetic satellites and Earth observation satellites to support this work directly, rather than sort of getting it off the back of satellites that were up there for other reasons. In fact, the real interest in the gravity field at that time was, in the early time, was to know how intercontinental ballistic missiles would move. So that was the driving Ministry of Defense type work that was going on at the time. But then it became more civil observations with Earth observation satellites. And we end up now, today, with this geoid from a satellite called Gochi, which was a dedicated satellite, needed some tracking from the ground, but essentially had onboard accelerometers. So it was able to sense gravity perturbations on its orbit from passing over regions of dense and lower dense regions. So by processing all those observations that were downloaded from the satellite, they were able to determine the spherical harmonic expansion, many terms, thousands of terms, to realize the actual shape of the Earth. And here we have, in this plot, we have the blue regions are regions of high relative gravity, which are interpreted as depressions. So high gravity means that the region on the Earth is closer to the center of the mass of the Earth. And in contrary, the red regions are highlands because they're further away from the center of the Earth, and the gravity is less than on average. So the whole scale of this plot that you can see there, this image, is about plus or minus 100 meters. And it's really the underlying gravity field of the Earth in the absence of tides, winds, sea surface changes, etc. So it's a perfect sort of reference frame underneath. And using this, one can then study ocean currents, ice mass changes, etc., by measuring gravity from a whole range of techniques, but you need to know what the Earth underlying shape is. So at that time also, there were growing numbers of observational techniques, and driven primarily with NASA's crustal dynamics project to monitor the dynamic Earth. Two techniques in particular were deployed from the late 1960s at a few sites worldwide. Now, at that time, the astronomers were using very long baseline interferometry. You can see on the plot on the left there, a technique using, in this instance, two radio telescopes pointing at the same quasar, which is sending out noise, random noise from the quasar. Both the telescopes pick this noise up and time at some high frequency, the noise against the time against the noise using a hydrogen maser clock, which is sort of accurate to a second in a million years, something like that. So a very stable frequency source. And you can see on the scheme here that the noise will arrive at a different time at those two telescopes as a function of how the distance between the telescopes is and how the Earth is oriented in space relative to the quasar. The radio astronomers were doing this work in order to map the radio sky. The geodesists then wanted to do that to measure the distance between the two telescopes. So that's very long baseline interferometry. And at the same time, the laser ranging technique was developed. The laser had been invented in the 50s, 60s. So very quickly, applications were developed. And the first laser range measurement to a satellite was carried out in 1964 at the Goddard Space Flight Center, where they had quite long laser pulses, but they were able to measure the distance to a satellite to an accuracy of a few meters, which was huge improvement in accuracy for that time. And it's obviously, you can see here, it's a very simple technique in principle. So the outgoing pulse is measured against a good clock again. A few milliseconds later, depending on the height of the satellite, the incoming pulse comes back, a few photons from that probably, and the clock is stopped, and the difference is the range in seconds is stop minus start, range in meters is stop, is range in seconds divided by this half the speed of light, multiplied by the speed of light over 2. And early results from these two independent techniques, which is the key really to this whole work, independent techniques, was confirmation of plate tectonic motion. For example, North American Eurasian plates are moving apart, the results showed, by about 17 millimeters a year. And here's an early plot from mid-84 with the Westford, which is on the east coast of the US, to Wetzel, which is in Germany, Bavaria. And the baseline is moving by about 17 millimeters a year. So there's a lot of noisy points on here relative to today's accuracies, but nonetheless, a very clear trend, which was the first confirmation actually that the theory of plate tectonics was indeed actually happening. And just as an aside, here's a trip we did to Iceland a few years ago, and on the right, I think it's North America, and on the left is Europe, and they're spreading apart at the beginning of this mid-Atlantic trench, which comes from Iceland way down into the middle of the North Atlantic, and is spreading the plates apart due to upwelling of magma along this crustal crack in the Earth's ridge, mid-Atlantic ridge. So two new techniques then were developed. We're moving forward now to the 1980s, 2000s, global navigation satellite systems. It's interesting to note that those two techniques I've just spoken about predated by a couple of decades, really, the GNSS, GPS that we all know and love now. which is very commonplace now, and it's part of the getting to understand the Earth system as a whole. And the principles here are that the satellites are transmitting time and position, and then the receivers are picking them up, solving for errors in both the receiver clock and in each satellite's clock. So you've got enough observations and enough satellites to return the coordinates of the receiver in the frame that it's provided by the satellite orbits. And that's what our phones are doing and our sat navs, etc., continuously. Another technique that was developed for particular satellites that have the equipment on board, which is a high frequency receiver again, are so-called DORAs, Doppler orbitography and radial positioning, integrated by satellite. That beacon there, on which there are 100 or so worldwide, transmits a very accurate or very stable frequency, and then a dozen or so different satellites, Earth observation satellites, pick that, record those signals, and the Doppler shift of the satellite moving relative to that fixed on the Earth system can then be downloaded to the ground, and that gives that Doppler shift gives the velocity of the satellite, which is another way of measuring its position. Okay, so we'll move on to Herstmonceux, which some of you, as you say, you visited there. The whole estate, the castle estate, is actually the campus of an international study centre funded and run by Queen's University, Kingston, Ontario. The whole castle, once the Royal Greenwich Observatory left the site, which I mentioned earlier in 1990, was purchased by an ex-student of Queen's University, and he granted it or gave it to his university on the understanding that it would be used as an outstation, in effect, where students could come do a range of undergraduate work, particularly related to European studies, etc. And that carries on and is thriving today, having had obviously a hiatus during COVID, but it's great to see now that the students are back and it's operating again. Anyway, I say the primary work of the Herstmonceux Geodetic Site is to run and operate a state-of-the-art laser ranging system. Now, nowadays, the ultra-short laser pulses, by which I mean about 10 picoseconds, which is a few millimeters long, at a rate of about 1,000 shots per second. And that gives the system the ability to range from low Earth orbit right up to geo. There's one geosynchronous satellite sitting over India, which have got reflectors on board, and the team can get returns from that in reasonably good conditions, when the conditions are reasonably good. And those observations are uploaded very rapidly, and I'll say more about the international sort of collaboration of that. Also, several GNSS receivers are operated on site. It's not just GPS, it's GLONASS, there's Galileo, the new European system, an Indian system, and a Chinese system that the receivers these days can get data from. So maybe 50 or to 100, almost 100 satellites over a course of 24 hours will be being observed by those receivers pretty much automatically. But key to their value at a geodetic site is accurate site ties between the laser ranger and the GNSS. And having those site ties as accurate on-the-ground measurements to link the two techniques allows accurate combination of the results, which we'll discuss. So here's the geodetic site. I like to call it Herstmonceux Geodetic Observatory. There's some discussion within the group, I know, and I'm not able to change things now, but I think Herstmonceux Geodetic Observatory sounds better than Space Geodesy Facility. But We were a facility funded by Natural Environment Research Council, but now we're part of the British Geological Survey as an observatory within its observatory networks, magnetic observatory, etc. So we have on the left there, the laser ranging telescope is in the third one on the right there. And we've got a couple of other astrometric type telescopes. The scale is, because the small one is close to you, it looks big, but the laser ranging one is clearly the biggest telescope. But in the middle there, we've got a 40 centimeter reflecting telescope working at Cassegrain with a Starlight Express camera, getting images of geostationary satellites relative to stars. And the one on the left there is relatively new, tracking LEO satellites optically. And it's a small aperture, 8 inch, and is under development to get rapid positions and brightnesses actually. And at the bottom there, a classic example of the laser ranging going on at night. I've got a couple of videos which are playing now showing this laser ranging system in operation. Clouds plague us all, but the observer there, the observers live quite close. So if the weather's going to clear at any time, day or night, they're able to come in and get things going. As the forecast says, the clouds are going to clear, which doesn't always turn out to be the case. But then a very capable system, this is obviously speeded up, very capable system of able to hop around and get track from many satellites that are on the schedule for that time. They can hop between satellites to maximize the use of this bit of clear sky, which is vital in this country to make the most of it. You can see there's some aircraft zoom by every so often, which brings me back to the radar that was discussed right at the beginning of this conversation with Bob. The radar and visual observer, so the person observing is up on that platform, looking out very carefully for aircraft, as well as receiving as a receiver for satellite for the signals from aircraft, which most aircraft have to have now, and that leads to a display of where aircraft are. I'll move on to the next one. And here's a day and night tracking in the summertime. Prove that it works in the daytime. Very clear sky there. Lack of contrails during COVID, I think. So the laser ranger is doing the same work as you saw on the previous one. It's transmitting very short pulses. The observer's hopping between satellites that are available, getting short bits of ranges from as many satellites as possible. And now into the night, and you see there are a few aircraft about, actually. This is probably pre-COVID. So hopefully that's given a flavour of what would be like if you were actually on the site. I just wanted to put some numbers to what I've been talking about. As I say, 1,000 shots per second. The time of emission is automatically recorded, and a counter is started, and the pulses contain about 10 to the 15 photons in a packet of energy about 2 millimeters long. And at that distance, I'm talking about GPS, ranging to GPS or GLONASS or Galileo, about 1 photon will make it back. And that photon may trigger, with a quantum efficiency of about 20%, the detector here shown on the right-hand side. It's a single photon avalanche diode. So it's gated just to be opened as that photons are expected to come back. about 30 meters in range before that photon is predicted to reach the detector. It's switched on, so it's able not to be completely overwhelmed by noise, particularly in daylight. And the little cluster here about of 8 reflectors are very frequently now put on low Earth orbiting satellites, all the Earth observation altimeter satellites, etc., have these clusters of cubes. So they give a very accurate and very strong signal back to the receiver. And here's it in action, how we know that our particular photon is the one we're detecting as opposed to noise. If one computes in real time the difference between the measured range, the observed range, and the predicted range, so the whole thing works on having reasonably good predictions, then those observed minus computed values will all tend to cluster around a track. As you can see on the top plot here, sort of a long time one. And in real time, this bar at the bottom is building up and a nice histogram form, so the observer knows that the pointing is good and the returns are coming in. And a flavor of a range of satellites that are tracked. So lower observation satellites, a whole load of altimeter satellites, the Jason 2 and Jason 3, they're making range measurements to the oceans. Sentinels are doing the same. Swarm is actually one of 3 which are up there to look at solar terrestrial work. But in fact, they have reflectors on board and they actually can be used for Earth gravity field determination as well. And then the geodetic satellites are spherical, ideally as massive as possible and as small as possible. The Lagioses 1 and 2, they are the primary ones, orbiting at about 6,000 kilometers above the Earth, which is almost a radius of the Earth above the Earth. And they're compact, 60 centimeters across, with several hundred of those retroreflecting spheres on them, cubes on them. And then lower ones, smaller ones, the Starlet and Stellar. And the Ethelons, which is what I did some work on quite a few years ago as a thesis, are up at the same height as the Russian GLONASS satellites, which are also mentioned on the bottom line there with the GNSS satellites. So GLONASS, Galileo, Chinese Beidou, the Indian IRNSS, and the Quasi Zenith satellite, which is a Japanese navigation system. There's a proliferation of nations wanting to have their own navigation capabilities. At the moment, no GPS satellites, no active ones, have retroreflectors, but NASA, in collaboration with the US Defense, has agreed to, there has been an agreement to put reflectors on future GPS satellites. So the global network of SLR stations, well, it's the first one notes is that most of the tracking stations are in the Northern Hemisphere. And that's really historical, how the technique grew and started up in the US, and then Europe got into it. And the Russians are very strong on laser ranging, primarily for tracking their GLONASS satellites and improving the clocks on those satellites. Because if you've got very accurate measurements from the ground to a satellite, and you also have the information about the clocks, one can check on the clocks and see how they're drifting with time, which all clocks will do. So that improves their ability to navigate globally using GLONASS only. So Herstmonceux in that group around Western Europe, and it's been given this tag. I've got the acronym ILRS, which is the International Laser Ranging Service, which I'll say a little bit more about, but it's a overarching part of the International Association of Geodesy, and the ILRS really sets standards of how many passes to be a member of the ILRS a station needs to track, what sort of accuracy is expected, and it collaborates on developing new technology and new analysis techniques, actually, about how to use this data and make it available to the wider community, the wider geodetic and geophysics community. I mentioned the Northern Hemisphere domination, but actually in the Southern Hemisphere, the Yarragadee is the most prolific station in the network, pulls its weight hugely, as does Mount Stromlo there on the east coast of Australia. South America has a couple of new systems, really not producing very much at the moment. Harty Beastock in South Africa is producing some really good data, and as are the US stations at Greenbelt and Monument Peak. So this is a plot of how well those stations, how much each station tracks. If you look at the green, there are the GNSS, so they track GLONASS and Galileo, for example. The Legios passes, which are the primary ones for geodetic work, determining station coordinates, are shown there in purple. And really, as I mentioned, Yarragadee dominates the amount of data, but Herstmonceux is producing a huge amount of very good data and always within the top few of the league there. The green horizontal line is where the ILRS, Laser Ranging Service, says you need to be tracking this number of satellites per year, number of passes, in order to be really contributing to this global enterprise. So there's maybe 15 stations are achieving that. Some out on the right there are new stations. Quite a number of them are the Russian stations, and we think they're doing their own tracking for their own purposes, but they get less invested in producing data for the ILRS, although they do what they do produce, and they're developing some new stations, is very encouraging. So the four techniques that I've discussed, the IGS, which is the GNSS organization, the VLBI, the laser ranging, and the Doris systems, essentially were doing their own thing up until in the late 1990s. But a NASA initiative in the early 2000s proposed that there should be a global geodetic observing system, GEOS, to set challenging standards and to bring all these techniques together to make valuable and to show that they're being driven by a science need. And the headline message that was promoted along with GEOS was that a global reference frame is required at an accuracy of 1 millimeter with a stability of about 0.1 millimeters per year. And the concept of core sites was promoted, where ideally all four techniques plus gravity measurement should be deployed worldwide, either completely new state-of-the-art or upgraded legacy sites. And with we'd already developed kilohertz laser. We'd had some funding from NERC and saw the way that the global network was going. We got funding for kilohertz from our old 10 shots per second, much less accurate and much less capable system. So we got SGF was given next generation laser status, but we only have GNSS, we don't have Doris. And there was a discussion about having a very strong transmitter in that part of the world. And actually Doris is a very well globally networked system. And there really wasn't a need for Doris, yet another Doris in Europe. But there was hope that, and still is, that we may get a VLBI system, so a large radio dish. And there is a new development of that that gives comparable accuracy to the laser ranging at the few millimeters level. So that's an ongoing, hopefully, improvement at Herstmonceux. And just some publications that came out of that. There's a GEOS requirements for core sites, which we've been showing our funding people, and also a nice book about why global geodetic observing system really is important for many, many applications worldwide. So exactly how this all works and how it all fits together is really summed up in this very nice schematic. So all of GEOS science is really summed up in this. So we have a altimeter satellite orbiting at, say, 800 or up to 1500 kilometers above the Earth. And it has an altimeter on board, which is measuring down to the surface of the ocean. It's also measuring water vapor to correct that altimeter measurement for delays through the atmosphere. And the name of the game then is to determine the satellite's orbit with respect to the geocenter to an accuracy of a centimeter or so. The satellite itself carries a Doris receiver. So there you see it tracking the Doris beacon, measuring that Doppler shift. A laser ranging station is ranging to it. And it's also seeing GPS or other GNSS satellites orbiting above the satellite. And the sea surface height is what is actually wanted. And you can see here with the working from the bottom, the ellipsoid is a standard ellipsoid shape of the Earth. The basic flattening, which I mentioned, the flattening of the Earth, that defines an ellipsoid. Then the ocean floor is a addition to that, with extra detail on that, of course, and it would be the same on the solid Earth with mountains and valleys, etc. And this geoid that's mentioned above the ellipsoid is that shape that the potato-shaped gravity field of the Earth that I showed you early on from the Gochi satellite. That's the geoid, and that's the equipotential surface that an ocean without any winds or tides, etc., would follow. It would sit on that geoid, and then all the ocean surface topography, winds, currents, etc., would be above that. So that, in a nutshell, is what we're doing when we're doing satellite geodesy. But of course, we need to know where those tracking stations are, and that's where the next parts come in. And I think I've said all that. But we've got to, as I say, determine the orbits and the tracking station coordinates within a high accuracy reference frame. The International Terrestrial Reference Frame is that reference frame, and that's been developed over many years and all the time improving. It's probably about a centimeter at the moment, slightly worse. But millimeter accuracy is required, and you'll see why. But there's many factors then to achieve that millimeter accuracy, and they're scientifically interesting in their own right. And here's another schematic showing really that the complexity of the Earth's wobbling in space. So it's spinning against its axis, but wobbling around. There's the core interacting with the solid Earth, which changes the rate of rotation of the Earth. Then we have, of course, solar and lunar gravitational attraction on the Earth. Winds are changing its spin rate, ocean currents, atmospheric loading. Crucially and interestingly, melting ice changes the dynamics of the satellite of the solid Earth, and therefore you can see how tracking the Earth, measuring the Earth, will feed into understanding more about melting ice. And there's a huge amount of information derived about groundwater, seasonal changes in groundwater, etc., which can be derived from generating this very accurate reference frame. So how do we do that? So say we've got a series of observations from a global network of laser ranging stations. We are able to essentially guess where the satellite is to start with and guess where each station is. And we're able to model to some fairly good accuracy all the forces acting on the satellite orbits. So if we are able to use those forces to integrate the satellite orbit, that yields a time-dependent X, Y, Z coordinates of the satellites in the same frame. In other words, in the center of mass of the Earth frame. And for each observational epoch at each station, the expected range is computed and compared with the observed range. And then there's a least squares adjustment in which many parameters are solved for and which will derive the instantaneous coordinates. And what usually happens is a 7-day orbital arc is computed, and there will be a set of coordinates derived on average over those 7 days, and the so-called Earth orientation parameters, which I'll point to in a moment. And we're currently doing that at Herstmonceux. Our analysis center package for that work has been built up at Herstmonceux over many years. So week-long solutions from 1983 to 2021 were submitted to a coordinating center, and in July, and that's ongoing, and there will be a new ITRF announced probably within 6 months or so. The technique contributions to ITRF, which I've sort of alluded to. So we have the 4 techniques, but the origin is uniquely realized through the coordinates of a global set of laser ranging stations. Those coordinates, as I say, are formed through precise orbit determination of the Lagios and Lagios 2 geodetic satellites. The scale, that's the size of this reference, determined through a combination of laser ranging and the VOBI, radio astronomy, and then all the other techniques give one the orientation of the reference of the Earth in space. The ITRF 2014, which is the most recently available frame, contains about 500 global sites. Clearly, the laser ranging stations are maximum number of 25, but the GNSS, there are hundreds of GNSS sites worldwide, DORIS sites, and a few tens of the VLBI systems. And our observations and our solutions, our orbit work, is in ITRF 2014, and as I say, will be in ITRF 2020. Okay, so this is the details are not that clear on here, the outlines of the continents, but essentially we're looking at down on Australia, and it's really just to give a flavor of the huge amount of information in that ITRF 2014, which of course, because the observations are carried out over many years, 20 years now, 30 years for the laser ranging, we have very good velocities of those sites, plate tectonic velocities, and rapid changes due to earthquakes, obviously. So this gives a flavor of what the velocity fields are looking like in the ITRF, where the scale there is about 1 centimeter, 2 centimeters per year for on my picture anyway, a 2 centimeter vector there, but very, very detailed. one can see subduction zones where matter is disappearing under at ridges, and plates are colliding. And from the altimeter measurements, which I showed you in that schematic, analyzed through a reference frame over many different satellites, in fact, from the mid-1990s, early 1990s, right up to now, through a whole load of different analysis centers using the radar data and doing their own orbit determination of the satellite, using every observation they can get, gives a very nice determination of sea level change of about 3.4, 3.3 millimeters per year, with bumps and signals in there showing changes in wind surface, wind patterns. Sometimes the rain changes, so it's raining on the land, where the dip there in 2011 was due to a strong seasonal signal in the southern hemisphere, where the rain was falling on land rather than in the sea. So it appeared that the rate of change of sea level height had decreased. But then once all that rain moved off of the land back into the sea, the trend continued and is continuing. There's interest now in knowing whether there's an acceleration term in that plot. And this is the sort of thing that's used by the climate change groups that are reporting just last week or so. So as I say, the weekly geocentric coordinates can be used to generate heights of the station, and it may yield information on seasonal geocentric motion, unmodeled loading, because there's a lot of loading measurements going into this work, atmospheric loading, sea loading, ocean loading, because in particular Herstmonceux is quite close to the ocean, the channel at least, and glacial isostatic adjustment, as was also called rebound. And then we can compare our observation with our solutions with other techniques, including GPS and absolute gravity. I should say I haven't mentioned in any detail whatsoever the gravity work that goes on in Herstmonceux. There was really, I could have spent a lot more time on that, but I think I wanted to concentrate on the satellite solutions for this. So this is our height time series, where we have plus or minus 100 millimeters there. Each point on here with its little error bar is the result of a 7-day orbital solution, as I've alluded to. And the overall slope from 93 to now is about 0.19 plus or minus 0.06 millimeters a year. And there is a model that suggests that the site should be, according to the model, decreasing in height by about 0.4 millimeters a year. So there is a difference, and we don't know why at the moment. And we've also got a new person working at Herstmonceux, who's a GPS expert, as well as becoming a laser ranging analyst expert. So we're comparing the heights from the GPS, one of the main systems at Herstmonceux, GPS, compared with our with the laser ranging heights. So we have variations there, seasonal variations, which are probably both local variations and modeling errors in both of those techniques, independent techniques. There's some modeling errors there somewhere. Very briefly here, there's a signal here in an 11-day gravity measurements in the basement at Herstmonceux. The green points are that. We've removed everything we knew about the ocean and local water level, because gravity is very sensitive to water table changes beneath it and indeed above it. But there's clearly some tidal-like term in that, and we're talking to BGS experts for what is actually happening subsurface. Is there another level of what's the sea doing way down below us, below our site, and driving a change in gravity? And this is important for gravity technique worldwide. They tend to go episodically to sites to measure their height changes. And if you're there for just a couple of days, you wouldn't see this kind of thing going on. So there'll be some systematic errors that we're trying to tease out, understand some more modeling that needs to be done. Just to show that it's not just Herstmonceux, we've done some work with colleagues in Australia. This is a similar plot from their Yarragadee system of height from the laser ranging. And again, we're not sure of the reason for a slope. It's 0.8 plus or minus 0.04, a very strong height change. So the station is sinking. And we are pretty convinced this is not systematics in the measurements itself, because we've allowed there to be systematics in the way we analyze the data. And there should be no global isostatic adjustment down in Australia. So there's perhaps hydrology beneath the surface where they're extracting water, for instance, but that's to be determined. And I mentioned Earth axis. I always find this quite interesting in the sense that it's a large signal. So if one was to go to the North Pole, stand where the spin axis of the Earth is coming up through the axis. But the Earth, on a couple of periods, but mainly annual, will move that spin axis position on an arc of about 12 meters over a course of a year. So the Earth is wobbling in space relative to its own spin axis, solid Earth. And that spin axis rate changes as well, the length of day. And these are obviously, we're talking about 12 meters and 10 meters or so, big signals for making measurements to satellites to a few millimeters accuracy. And here's a length of day. So length of day relative to 86400 seconds in a day. So we've got a strong seasonal signals in those length of days, which are of interest in their own right. What's driving them? And some work done way back in the RGO showed that the main reason for length of day varying is atmospheric angular momentum exchange. So the atmosphere of the Earth drives the solid Earth to some extent, or changes the rate of rotation of the solid Earth. And because that's seasonal, northern hemisphere and southern hemisphere, winter and summer differences, you can get an annual signal in the length of day. So there's a direct link, and it's been shown properly in terms of the modelers, the atmospheric angular momentum people, were essentially weather forecasting techniques, looking at the whole atmosphere's motion and energy in the atmosphere. And there's practical reasons for knowing this sort of thing, because if you want to communicate between ground stations and planetary spacecraft, accurately pointing the antennae, for instance, one needs to know where the Earth is pointing. And then the decisions on whether to insert a leap second into atomic clock-based international timescale, which one could, and there has been a debate about whether one should forget the Earth, in a sense, for clocks, use atomic time throughout, which is accurate over decades and millennia, in fact. But then we've got the Earth getting out of step with that potentially. And so there probably would need to be a leap hour at some point in 10,000 years or something. So at the moment, I understand the international community is going to keep the leap seconds that are put in either in July or December and cause havoc in predict in our processing, because suddenly there's a change of time in all the observations by 1 second. And in much longer term context, length of day, this is some work done by an ex-member of the Royal Greenwich Observatory, where they, in a collaboration with people from Durham University, where they're using ancient eclipse and occultation timings from as many places as they could get. And they were able to amazingly go back to 2000 BC and determine the length of the day then. So the plot is showing there's a long-term trend, giving an average slowdown of the Earth of about 1.7 milliseconds per century. But the tidal friction, that is the fact that the Earth and the Moon are locked, or the Moon is locked in terms of its spin. There is because of conservation momentum, the Earth spin gets slightly ahead of the Moon, and there's a drag then on the Earth, slowing it down. And as I say, because of conservation of momentum, the Moon is going out, and we know it's going out, not from theory, about 3 centimeters a year, but from laser ranging measurements carried out primarily in McDonald Observatory in the US. So there's the tidal friction on this plot doesn't show the whole story. There's other things going on. And it's really the fact that the post-glacial rebound is changing the shape of the Earth. And that change of flattening of the Earth will change the angular momentum of the Earth, and therefore the spin rate. And that's been very well determined. You see the high frequency data, plenty of data in the current epoch there, about the end of that trend, but it fits in very well. So are we there? Are we at a millimeter? When the ITRF was constructed, a combination of all 4 techniques, the scale was determined by the arithmetic mean of the implicit scales of laser ranging and VRBF solutions separate. And it was found that there was a systematic difference between these of 1.4 parts per billion, which is about 8 millimeters. So systematic, when you're worrying about millimeter accuracy, 8 millimeters is quite a lot. And here we are, the 2 scales, VLBI above the laser ranging. And we looked at this particularly on the point of view of the laser ranging. We asked the question could there be systematics in the laser ranging causing that? And indeed there is. Most sites really don't measure to the satellites to the millimeter precision or millimeter accuracy that their precision would suggest. So we published some stuff on that, and it makes a much better agreement between the 2 scales. But it's, and so that was quite useful and has changed the way the processing is carried out now. There is an awareness that the laser ranging isn't perfect, but it's close. So why bother with all this? This precise frame is used by a huge number of individuals, and crucially, whether they're aware or not, it becomes something that one uses. So say surveying, aircraft navigation, vehicle sat-nav, huge amount of automatic crop harvesting. I know they're doing in Australia in particular. They need to know, and interestingly, actually, aside for Australia, Australia's moving at a rate of about 7 centimeters per year due to plate tectonics. So over 10 years, that's 70 centimeters, that's more than half a meter. And if they're running their automatic crop harvesting, that's something that they can't put up with. So they need an updating reference frame. They need to know these velocities. So all these applications then depend upon and are based on the underpinning reference frame. And the crucial thing recently was that this has been recognized at UN level with representations from this GEOS organization. So the UN has recognized that many nations still use their own internal reference frame that can be tens or hundreds of meters off from a consistent global frame. So they adopted a resolution saying that the global reference frame, global geodetic reference frame, they don't like the word international in UN speak, is a generic term defining the framework which allows all users to precisely determine express locations on the Earth, as well as to quantify changes in the Earth and space and time. So the GGRF is realized through the ITRF that I've been talking about, as well as the International Celestial Reference Frame and some physical heights system. So crucially, where this geodetic technique is now well into the publicity that comes and realization that comes with UN resolutions. There was a virtual event on Earth Day this year, where many leaders of member states, representatives from member states, got together and recognized the need for this kind of work. So in particular, to measure things like causes and effects of sea levels, storm surges, earthquakes and tsunamis, etc. And to end, then some quotes from the wider geodetic community. It is really quite a wide community now. And they had that Global Geodesy Forum on Earth Day, the power of where they called it. And it was a virtual because we were still COVID restricted. And a lot of good discussions were put, not just the sort of admin side, but lots of science was developed and presented rather here. And notice on the right there's an updated mass loss animation for Greenland and Antarctica has come out of gravity field satellites that are tracking the gravity field and are very sensitive to changes in ice mass, because that changes the gravity field as sensed from those satellites. So there's improvements in how many gigatons per year are being lost from the ice sheets. So geodesy underpins much Earth observation, remote sensing work. Accurate tracking leads to a consistent reference frame. And interestingly, the Earth is very much a dynamic system of processes occurring on short and long-term scales. And I hope to have given you a flavour. They're actually interesting to study in their own right, but also feed into policy, which is regarding climate change, which is crucial, I feel. Okay, the operational work of Herstmonceux, which hopefully in the future you'll be able to come and see, is given on that website. I think I would end there.
Thank you, Graham. That was fascinating. Open up to questions from the audience. I see Bill Dave's got his hand up, so go ahead, Dave.
Hi there. That's great talk. Thanks, Graham. Question there. I was watching a program recently on telly about how the big corporates, particularly for the farming communities across the world, Australia included in that, were extracting vast quantities of water from the aquifers far faster than the aquifers are actually naturally being replenished. So I would assume that there's quite a telling mark on some of your data of that actually happening.
Yes, I think that's right. I think particularly Australia, they're concerned that downward trend in the height could well be due to aquifer. So any measurements of that is very valuable. I mean, of course, people have to have water, but any measurements of how much is valuable. And we're looking, the Australians themselves, in having seen our plots about their heights, are looking at other measurements like gravity measurements, etc., and seeing if they can collaborate all that.
Yeah, I think part of the political statement being made by that program was that water is a global commodity, and the big corporates are stealing more than their fair share without telling anybody.
Yes, that's right. It's the without telling anyone it's the problem, isn't it? Yeah, I mean, I think places like Las Vegas are huge.
Yeah, that was one of them. Yeah,
pumpable, people pumping out a lot of water there.
Yeah,
water is going to be a big issue, isn't it? As well as migration from places which are going underwater.
Yeah, because we're talking freshwater here and or contamination of freshwater reserves. Yeah. Thanks.
Yes. Yeah, scary.
So Jill, you had your hand up briefly. Do you have a question? Jill's gone quiet.
Sorry, no, I was just clapping.
Okay.
Sorry. I'm actually still at work at the moment, so I'm working while listening to the talk.
So anybody else with any questions?
I've got another one. If I may, there was no noises being made. The other one is when I was watching some of your video, I noticed that when the laser was spinning around doing its thing, most of the times, obviously, we're only seeing a very fine line, but other times it was quite a broad spread beam. I wonder if you could explain that bit.
Yes, that's an illusion in the sense of the fact that it's a speeded up video, and it was almost certainly a low orbiting satellite, so it was very quick.
Yeah.
Tracking of that satellite, so it just sort of fans out.
So you get the wavy hand sprinkler effect.
Yeah.
You get the wavy hand sprinkler, yes, and of course all that bright beam is wasted photons that are not going up to the satellite.
Yeah.
And in fact, we've used a LiDAR technique. Again, I didn't have time to talk about everything, but another person there set up a system to measure the heights of those photons that are coming back from the atmosphere. And they got it going just in time for the unpronounceable Icelandic ash event that came over us. And we were able to measure quite well the distribution of the ash vertically above Herstmonceux, sort of a few kilometers up. So it's another technique which is there, but
that was also
uses.
That was also spoken about on a more recent one about the damage to aircraft engines, given that the density of the volcanic ash makes it virtually invisible to the naked eye. And so that was a panic moment when aircraft engines were looking as though they were putting out searchlights in front of them. And that was due to the,
as soon as I heard that the ash was coming, sort of thing, we got this new system going, and then the Met Office actually contacted us and said, can you make as many measurements as possible during this period, because they were using other techniques, color of the sky and that sort of thing, as well as LiDAR. So it was an interesting time.
It's fascinating how much spin-off science comes out of a basic principle that's been going for a long time, and then you suddenly get the alternatives, things you can do with it.
Indeed, yeah.
And of course, the other connection with Herstmonceux and astronomy is the William Hersch and the Isaac Newton telescopes that left for La Palma.
Yeah.
And of course, the current events in La Palma with, I think the number of frequency of earthquakes has subsided from the peak, but certainly hundreds, sort of between magnitude 3 and 5 at the moment. And sort of hear reports of various stations measuring sort of centimeter uplifts in certain parts of the island. And of course, it's interesting the fact that obviously the observatories are located on the old Tabarante caldera. But I guess the question is going to be is that, presumably in terms of the frame, they would get to see any shift in their altitude based on current events.
Yeah, it'd be really good to have a geodetic site there. I mean, I know they've got GPS everywhere, because there's that worry that if a cliff on La Palma crashes into the ocean, it breaks off and crashes in, which potentially it would, you'd have a tsunami going across to the east coast of the US. That's modeled to be the case anyway. So there's a lot of there, but it'd be good to have something like the Herstmonceux system there. And I believe there is one going to Tenerife. I'm not sure who's running that, but there is going to be a geodetic site, laser ranging and other things on Tenerife, because the weather will be so much better than Herstmonceux.
Yeah. I seem to remember a couple of years ago when a crowd of us were there, they were doing some laser testing between La Palma and Tenerife.
Oh, well, you've been there. Okay.
Yeah, we had access to the Mons, which was really good.
Mm. Yeah. Oh my gosh.
So, John, have you got any questions? Sorry. So, JBS, you sort of popped up on there. You got a question?
Yes, I did have a question. With plate tectonics, it means that all the stations, all the observatories are swimming around on the surface of the Earth. How do you measure anything when everything is moving? Is there a spot that we say is spot 0 and everything else we measure relative to that? Or is you know, how do you measure when the whole thing is all wobbly?
Sure. Yes, I mean that's the interest, isn't it? For the laser ranging and the other techniques, actually, the geocenter is the point at which the satellites orbit. So that's the origin of the reference frame. And then you can, as I say, you can determine the coordinates relative to that of every station on a weekly basis. And during that week, not much happens unless there's an earthquake, of course. And we have some examples of rapid change, like on the west coast of the US and Japan more recently. But essentially over that week, nothing much happens. So you get an instantaneous or an average value that week, and then you look at the next week and next week, from which a smooth or not smooth velocity comes out for that particular station, for all the stations. And the reason the laser ranging is particularly sensitive to the Earth's origin, central mass of the Earth, is it's a very clean measurement. You're just measuring range. There are some corrections for delay through the atmosphere, but compared to GPS, where there's many, many corrections, I mentioned the clock errors on the satellites. There has to be a lot of averaging and differencing of the GPS measurements. And you lose that connection, that strong connection to the geocenter over that period, for that reason rather. So everything hangs on the geocenter driven by the laser ranger. Of course, where's the origin longitude-wise is a different thing. It used to be that one would say, okay, this station has a particular longitude, a map, then we'll let all the other stations be relative to that. But now there's a link using quasars to an absolute origin, mapped to Greenwich actually, but not that there's an observatory at Greenwich, but that's the less well-defined longitude-wise. But that's really just a rotation. You can shift all the stations because there's no absolute orbit plane, but there is an origin absolute. So it does work in that sense.
So that means ultimately we reference to quasars.
Yes, they are the almost ultimate inertial reference frame.
Wow.
Although they're finding, they're point sources, although some sources are not point because the accuracy of the VLBI now is such that they can determine structure. But essentially, if you use the point, the hotspot of a quasar, that's the external reference frame for the celestial reference frame. And then the terrestrial reference frame needs the laser ranger for the origin.
Yeah. Wow. Thank you.
Yep. So we have no further questions. So if we could do the usual and give Graham a round of applause and appreciation for that excellent talk.
Thank you very much. It's been a pleasure to speak to you.